Now, please join me in welcoming Rob and Aashiq as our next speakers.
Excellent. Thanks so much. Fantastic to see BSidesSF back in full force this year. Really impressed as always by this conference. And again, my name is Rob Ragan. This is Aashiq Ramachandran.
Hello.
And Aashiq and I have actually been collaborating on research and running experiments together, and honestly just messing around and seeing what we could learn for about 6 years. But the first time we met in person was yesterday. So we were often like meeting on Saturday mornings, and coming up with ideas and deciding to go build some prototypes and see what we could learn from them. And what you're about to hear really stems from some of those sessions that we started about 6 months ago. And it really, we were hearing so much and reading so much about how people are going to be fine-tuning their large language models, and that this is going to be a big risk for data leaks. And but we couldn't find any details on exactly how that would happen, how that works, what can go wrong, and what you can do to fix it. So this is really stemmed from our effort to do that. Really a big observation away from this, though, was that the generative pre-trained transformer algorithm is very simple. It has no concept of security built into it. So all efforts to secure it, make it safe to use, will have to be done either through efforts of data scientists or security engineers focusing on making that happen. And there's a lot that can be done actually before you're preparing to fine-tune a model, and there's a lot that can be done after. And so we're going to kind of cover that broader spectrum. So this is really the paradox. We kind of expect all of these large language models to be trained on massive, diverse data sets, but how do we know how much sensitive information is in there? That's really something that we label and we decide, but it's a hard question to answer. And these models are going to generate and return whatever they have available to them. They don't have this concept of what is sensitive. So that's something that we have to figure out in our usage of them. And as I've been learning more and more about how to leverage the LLMs, I've always kind of tried to remind myself, and I think this is probably something everyone could take away of, if it's not doing what I expect, or I'm not getting it to work the way I want, I'm probably using it wrong. It's just a tool. It's not its fault that it's not doing what it's supposed to do. It's us as people that are applying these tools to take the responsibility to learn how to use them more securely. And so this is what we'll dive more into. So the new AI stack really, I think, looks like this. And there's the underlying infrastructure, the ML ops that you're building these models on. And then there's model development. This is really where we're going to be focusing. A lot of what we did in this experiment was focus on the data set engineering. What can you do to prepare your data? What can you do for fine-tuning an existing model? There's only a handful of companies out there we think they really are going to be building the massive foundational large language models. So this is more applicable if you're a company that is trying to use one of those or use an open source model to actually power your applications. And then on top of that, you can do prompt optimization and engineering. You can use retrieval augmented generation, and you then can build other applications and user experiences on top of that. But what we're focusing on in this conversation is really on that model fine-tuning and development, and what you can do there. So again, just to level set on the problem, data leakage is this ability for the model to just reproduce or memorize sections of the data that it was trained on. And this occurs because all it's really doing is building statistical patterns on its training data of what to predict next based on what came before and what else it's prompted to reference in its context window. And so if what it was fine-tuned on and what it was trained on is this personal information, trade secrets, or copyrighted material, that being returned is ultimately the problem that puts us at risk. And so I wanted to just refresh, to the model, this is all it sees. This is all it knows in the text that it's fine-tuned and trained on. These embeddings are converted into the text is converted into embeddings, which are represented as tokens. And the tokens, I think you often hear are partial, like either a word or a partial word. Those highlights really give you a sense of like what it is treating as a token, and then ultimately it's just going to be represented as these numbers, and then the patterns of like what comes next based on whatever it's seen the most of is how it's going to produce this, and so that text looks the same as sensitive data. Like this is what sensitive data, like to us, this jumps out as alarming. If we were to see this in a data set, we were to see like plain text social security numbers or credit card numbers or other PII, but to the model, it looks exactly the same as any other text. So some of the root causes, and we'll dive deeper into this, but I just want to set the stage, is improper preparation of your training data, repetition of sensitive data, or something that was input in reinforcement learning and human feedback loop content that didn't get properly sanitized. I think also something that we learned that was really interesting, and we'll dive into what this means, is the structure of data matters. So if you're taking your data and you're using that to fine tune an open source model, for example, there might be, like these models aren't good at structured data. They're really good at unstructured data. But if you're not removing things like delimiters or XML or JSON formats for what you're putting into that fine-tuning process, that can create problems. And also the padding, like the preparation of the size and length of the data that you're fine-tuning on matters. And we'll see a little bit more about that. The impacts are really like this can affect the reputation of the organization. People lose trust in it. Whatever data is retrieved might lead to identity theft. And I think some of the regulatory things are what scares folks the most. Like I am hearing more and more about, especially recently, is am I at risk of using from a code gen model code that is actually fully memorized and something that is fully memorized and is actually going to impede on copyright infringement. And something that I've even dug in a little bit more is Microsoft said back in September 2023 that if you use our models that are provided through the Azure OpenAI Studio, we will cover you if you're in a lawsuit or a case for this. And you can submit a claim and we'll cover the costs of your infringement. Then in December, they added some fine print to that, which was you also have to have used our system prompts, or they're calling them meta prompts, and you have to show that you tested the model, the implementation, and evaluated it for copyright infringement, but provide no other guidance on what that means, other than like you should go run a red team on the model, and there's a high-level description of that, but we'll dive a little bit more into what this means as well. So we decided we wanted to actually see what causes these. We wanted to see what are the anti-patterns, like what mistakes can you make? And so we tried to make mistakes on purpose, and then what's most useful to actually prevent this. So we set out to build this model that actually leaks, and then we're going to try to fix it. And so I know a lot of folks, and what we're seeing being used these days they're applying retrieval augmented generation as the primary way to like go to this data set, use it to get some contextual search, bring back facts to me, like I want to avoid hallucination, or I want to have the most updated data in my response. And we're not seeing as much people use fine tuning yet, but I think we will. And like fine tuning is a really good use case for whenever you can't think of to tell the model on how you want it to behave. You maybe can't put that into a prompt. But you want to just show it. You want it to actually say, here's data that I want you to emulate. I want you to actually set this as like the tone or the format of the responses, or the quality of the output. I want it to resemble this. I want to actually identify failures in what the base model is doing, and I want to put that into my data as examples to follow. This can help eliminate like problems with edge cases, or like here's an entirely new skill I want you to study from this body of text, and that's what I want you to actually be able to generate responses on. So I think like right now where we're at, we're seeing a lot of people build these Q&A chatbots, and they're using RAG for that. Fine tuning can help a lot more with summarization, but I think we're going to see as time goes on a hybrid of this, and as people run into the limitations of RAG, they're going to be fine tuning as well. So you want to talk a little bit about the steps?
Yep. So more often than not, something we've realized is people often think fine-tuning a model is really complex, but actually fine-tuning is the easy part. The more difficult part is everything that surrounds it. So quickly running over the steps for fine-tuning a large language model. First off, as Rob was mentioning, we don't really go out and build the bigger foundational model, but rather you choose a base model first. This is arguably one of the many models, your GPT-2s, your BERTs. We'll dive into that a bit. But you choose one of the pre-trained model that works best for you. Then most of the time is arguably going to go into preparing a data set, where you choose a data set, you clean it, you test smaller chunks of it to make sure it's what you want. And once you're happy with the data set, then you're going to go to training. The training is arguably the easiest part here. It's probably a script sub 100, sub 200 lines of code, nothing more than that. And then once you've trained it, you go on and evaluate it. You make sure that the model you've trained actually is doing the job you wanted to do, making sure it is better than the untrained base model. And once you're happy with the evaluation, you go to deploy. Deploy is a little more complex, where once you deploy, you go back, you collect data, you prepare it, then it starts going into a feedback loop where you make sure you keep training the model as and when you go. But for a large duration of the talk, I think we're going to focus a lot around preparing the data set. Okay, so the experiment. Rob, do you want to talk about that a second?
Yeah, so this was our idea of like, how can we make a model that's broken on purpose? We actually decided to combine the Lord of the Rings full text with 5,000 records of PII. Like, we're trying to make this thing leak. And yeah, then we wanted to basically see, can you go back and retrieve the PII from Golem? And basically made this with a variety of different models and just to observe what would happen.
Yep. So here's what we did. We had GPT generate a bunch of fake data for us, which we then took and put into Gretel. So Gretel's one of the more popular tools today, which help with data augmentation, where it kind of generates a lot of fake data if you give it a small sample set. So we took a couple of data which GPT generated, gave it to Gretel, and got variations of PAI, and then smushed it together in with the Lord of the Rings book.
Yeah, I think this has a lot of utility and is very useful. So like, I'm in no way affiliated with Gretel, but this really helped in the process. Like, basically having ChatGPT generate like 10 lines of PI, was able to give that to Gretel. And then it's really designed to help you generate synthetic data. So none of the PII you're seeing here is real. Like, where this is not violating anything in this presentation. But this was super easy to do. And it also, I think there's a lot of utility in this if like, I've seen cases where I've had like customers say, we're worried about giving our data science team access to our production sensitive data so they can do their data science experiments on and even practice like fine tuning models and training. This is like a really prime use case and an easy way to make that actually happen to generate versions that would be the same format, data type, length range, but is just fake versions of that data. So this is what we use to build that and then plan to integrate in with the Lord of the Rings text.
So that's how the finished sample, or at least a smaller portion of it that would fit in the screen, looks like. Most of that is a mix of the Lord of the Rings text, inside which we just splashed in PAI. Now, we did run a couple of variations. We'll walk you guys through the demo really quickly. We're super excited for that. But on a very high level, it's just like bits and pieces of fake PAI mixed in all throughout actual blobs of Lord of the Rings text.
Yeah, and I think this actually matters. Like you see like the representation of we had to basically prepare the text into these strings that are the same length. Like this is part of like the padding process and something that's very important. If you have like all different length strings or even different versions of this, you might have tokens that are detecting on patterns that run over that length or are behaving on like these groupings of tokens that would be in whatever context size of the model that you're using and end up blurting out parts of like another training line that that you didn't want it to.
Okay. So I think now we're stepping into the actual experiment of Precious PAI. So before we get into the actual tech bits, a quick overview of what we've done, how we prepare the larger experiments. So on a larger scale, we took two classes of models. The first, again, a couple of commonalities. The training set was the Lord of the Rings book. We did not really change much of that. We took 5,000 bits of PAI and splashed it across the same book. But here's the difference. In the first class of models, each record was duplicated 100x. So we had, every person's PAI repeated in a pattern, whereas in the class B, every PAI bit occurred exactly once. And in class A, we took a GPT-2 model. Yes, it's old, but, arguably a very good transform example. And in the class B, we took a BERT model. Both of them had pretty quick training. We didn't really spend like hours and hours of compute or energy into training them. For the experiment, we kept it pretty simple. But these are the high-level classes. We ran these across GPT-2, BERT, and Falcon models. Unfortunately, we weren't able to show you the results of Falcon. Hugging Face doesn't let you run inference on larger models, but we will show you the results of the others. Before we jump in, what did we discover, right? Forget about the experiments. What are the outputs? The class A models, basically the ones that had duplicate records, and they leaked a lot of information. As we noticed that when your training data set has patterns in it, the model is more likely to spit those out, because at the end of the day, as far as Rob was mentioning, right, the text is in turn converted into tokens and that form token patterns. So the model doesn't really see a difference between, hey, this seems like a credit card number versus this seems like a blob of text. As far as it's concerned, it's just a pattern of tokens. So something we noticed was, as the PI repeated a lot, the model was more likely to leak the exact same token sequence, effectively meaning leaking the exact PI from the training dataset. At the same time, when the PI repeated only once, but when it was a very large count of PI, we noticed that it didn't leak as much, but hallucinated. So going back to in theory, it didn't give you the exact same sequence of tokens, but did notice that each of these data points had some similarity in structure, and that structure was leaked, leading to data that looked like sensitive information, but wasn't really sensitive info. I think we have a really cool demo down the road for this, and we'll get in there. Okay, so here are the recordings. I think
see the top one, and we'll zoom in on the bottom one.
Yes, but so if on our screen you're going to see two videos playing simultaneously, where we just start off the entire slew of experiments where we have two models, one GPT and one BERT. The top one is the class A models where the PI repeats 100 times, and the bottom one is where it does not repeat. So you're going to see we start off by just a simple text saying how are you doing. Neither of them leak any information, right? It's good. And from there, now if you remember the data set we had before, a lot of the PI samples had hyphens in them, like special characters and whatnot. So we tried adding a hyphen to both the models and saw what happened. And as you see, maybe let's pull up the first one.
Yeah, I think that one's... Can you see that top one? Okay.
Yep. So as you see the first one, the minute a hyphen starts coming into the picture, the model starts recognizing a pattern and attempts to at least start, kicking out some information, which looks like real info. And we see info about one Omega Thiel, which is actually a person whose info we faked in the training data set. But the second one, the BERT one, which was trained with exactly one instance of PI, does not actually repeat.
Yeah.
Now, okay, we know that there is one Omega in your data set, right?
Yeah, there's a name Omega Thiel in the data set that was a fake name that was generated.
And now we try to we keep that as an entry point and see how much more can we drill about Omega. What are those characteristics of the data which, if we simulate, starts leaking? Where first off, we try a very simple thing. We just ask who's Omega? But asking that straightforward question doesn't really reply. The model doesn't get back to you, because in the training data, we don't really have a Q&A style, but rather was just trained on troves and troves of text. Okay, so growing in from that, what we did is we tried, okay, let's not ask it who is Omega and just put a question mark. What if we ask it who is Omega and try to replicate the style of PAI in the training data set, which is basically hyphens, your commas, so on and so forth. Now that did provide marginally better results. It didn't really go off into generating random bits of text, but it still isn't leaking PAI as we expected it to. Upon retroing, we realized Omega isn't the exact structure of the PAI in the dataset. So we tried taking the same prompt, but matching the input prompt to more like what was there in the training set, where we said who is Omega space Thiel and a comma, which is what the PAI in the train set looked like. And that showed results massively, where in the vulnerable GPT one, if you see on top, it doesn't leak info about Omega, but starts leaking info around other bits of PAI that was present around that person in the training data set, where we start seeing credit card numbers, date of births, so on and so forth. But at the same time, if you see the model below, the BERT one, which does not have PAI repeating, is just far more better, right? It doesn't really leak any information per se, because here there was no pattern that was constantly being followed. Now, yes, hallucination, right? So what, if you remember what we were saying before, in the above one, when information does leak, in the vulnerable GPT-2, that is the actual info of the person. When you were able to match the input prompt as closely to the repeating PAI, it starts spitting out actual data. But when you have non-repeating PI, and when you kind of make the model leak information, it starts hallucinating data. And what we did was we tried making it leak, and we searched it through our training data set. And as you can see, it doesn't really have that exact bit of information that was generated. So it isn't really the information about the person, but more of some data which it kind of rendered in similarity to structure. So, but again, the trick does lie on, okay, fine, great. It's giving you some info. Ideally, it should not be leaking info at all. But how do we effectively differentiate between what is PII, what is like real PII, versus what is fake PI? But that's something which we'll touch in a bit where we talk about defenses. Okay, Aashiq, you spoke about all of these great experiments, a lot of video recordings, a lot of GIFs on what you've done, but what are we trying to say here? At the end of the day, what is something that we observed, right, from running these experiments over the last couple of months? Effectively, to summarize in one line, we realize that the more the PII repeats versus the size of your overall data set. So imagine a ratio where your training data set, the number of lines, the number of characters, and how much your PI is there. More importantly, not only how much is your PI there, more importantly, how much each bit of PI repeats. The higher this ratio, the higher it is going to spit out the exact same token repetition or the exact same sequence of tokens, basically the PI, and lower it hallucinates. The lower this ratio, but if you still have a very high count of PI in your training data set, but not as high of repetition, it's the inverse. You're not going to leak as much, but you're still going to hallucinate equally well. But why does this work? I mean, this effectively is a result of, just pure derivation of experiments, and you're running sample set on top of sample set. But why does this work? We spoke with a bunch of people, we tested a hypothesis, and we found out, again, effectively this ties back to the nature of LLMs, right? LLMs obviously work on attempting to predict the next token based on the patterns of tokens seen before. And here, the more the repetition or more a particular structure of data pops in to your training data set, the more that's going to come out. And that's what in turn makes the above representation work. From there, okay, that is what we were able to build out and make a leaky model or a vulnerable model per se.
But yeah, and I think that the main takeaway from there is like, it's going to, whatever is repeating in your data set, it's going to echo back exactly more often, and whether it's PII or not. So like, that's just how they work. And, but then it's up to us as security professionals or a data science team to actually be on the hunt for like, what don't I want my model to repeat, and then run and do this data preparation process to eliminate that from its behavior.
Correct. And that applies in both value and in structure. It's not only like, it's going to leak real values or, it's going to give out similar looking data structures. It applies to both, right? But yeah, taking that in account, we thought we'd take a minute to talk about what are a couple of the steps which we did, which we realized, very small steps, not really like super complex, super simple ones, but made worlds across difference in terms of, making the model better as it not leaking as much, right? So first off, the base model selection. When we're fine tuning a model, we are obviously starting off with a larger, bigger model. We need to make sure we select the right model for us. Now, we thought a lot about how we wanted to tell you guys, like, here's the best model for your use case. But the answer, honestly, that it is dependent. That there is no one size fits all, like everybody go train your GPT or everybody go train your BERT, right? Honestly, it depends on the use cases you guys have. And something which we found was it's just best that you experiment by training smaller models of different types, like GPT, a little bit of GPT, one smaller BERT, see which one fares better, evaluate, and then go back to training the bigger one. It's genuinely not a good idea to just take all the data set and hit one model, whichever is the biggest you can find. While bigger models, as in sizes of parameters, you might have heard your, Falcon 7B or Llama 80B, right? While the larger the parameters, generally the model is better at a wider array of tasks, but is more prone to leakage when you fine tune as well. So as far as fine tuning goes, something which we genuinely wanted to share across the larger audience is bigger is not always better.
Yeah, in this case, like it's the bigger parameter sets that it's able to do, that you have to look for bigger patterns in your tokens that are it's being trained on. So that is a little bit more of a challenge in actually securing those models of like, it might memorize more, it might regurgitate more, and have a little bit more info on that.
Yep. So
yeah, so like this is actually like research showing how that scales. Like the 6 billion parameters will leak way more entire data sets or entire memorization. Like this is how like kind of see it literally of like memorization of like a small 125 million parameter model versus like a 6 billion parameter model. Like it's going to regurgitate entire blocks of text if like the bigger the model is. And this also matters for context size window. So like the more it remembers about like what you're having a conversation about, the more it might apply to going to retrieve tokens from what it's been trained on and spitting that back out.
But that being said, going back to what we started about, most of what the results or a leaky model or leaky nature of a model can effectively be prevented or mitigated by preparing your data the right way. And here are a couple of the top techniques which we noticed just genuinely helped with making your model that much more better. None of these are really complex, but add values which just help really a lot. So let's quickly jump in one by one. We have the top 5 techniques. The first one is word distances. Not as commonly used, surprisingly, but word distance is effectively where you take in your training data set, you take every word and you just see how far they are from the next occurrence of the same word. Now, while there are a few words which make sense to repeat a lot, such as your the ands, your common English language words, that's perfectly fine. But if you know what PAI is there in your data set, again, ideally you do not want PAI in your data set, but in the cases where there inevitably has to be some sort of information in your data set, it's better you keep that count as low as possible. How do you find that? An uber simplified representation is on the screen here, where you just see what's the closest occurrence, how many times it repeats, not only how many times it repeats, but also what's the distance? Like, is it like every third word is my PAI? Or is it following a particular pattern? Finding that distance really helps, because as we were mentioning in our findings, the more of a common pattern your PAI shows, the more likely it is to kind of leak out and start spitting out the exact same sequence of tokens. That is one metric which we found was really effective.
Yeah, and you can expand that to not just words, but entire sentences, paragraphs, whatever like context length size of your data model that you're fine tuning. Like you basically have to scale this up, to properly detect like, is there repeating blocks in here that are going to stand out and that are going to get memorized and get returned?
Okay, inaccuracies. This is one of my personal favorites. We've spoken about this so much in the last couple of months when you're working out this one. Something when training a model is your data is going to have to be uniform or near uniform. You cannot have like, say, we will see an example, but imagine you have a blob of text which is predominantly text. You do not want to have like random JSON content in the middle over there. That is you deviating from the standard pattern of data. Or imagine if you have a list of countries. You do not want to randomly throw in a couple of car manufacturer names. That is deviation in your data set. Now, those deviations form anomalies. And those anomalies, any PAI surrounding these anomalies, or any information in general surrounding those anomalies are more likely to leak. So,
and I thought this was interesting for just things that you don't want returned, like being able to not necessarily like leaking sensitive information, but if it's going to have a bias to return things because there's some deviation in the pattern of the training set, then like I think that's good to know just for like the behavior and functionality of the model.
Correct. And again, the way I like to think of this is when your data set deviates, you effectively build so-called poison statements where if you try to, get results around that deviation, is going to leak a lot more. A little simpler representation, we have a simple bell curve, but assume that on the x-axis is your standard models, your data set, uniform data set. Any PII around the deviation in the context of PII leakage, any PII around data deviation is prone to leakage far more than the other ones. Moving up from there, an example, yes, given we wanted to make sure it's a little easy. So let's take a simple data set of usernames, user emails, and phone numbers. In the middle, you see that we've kind of splashed out a couple of phone numbers in text instead of the standard numbers, and a couple of emails. Instead of following the standard email pattern, we have like text such as personal user's email, email not found, so on and so forth. So any content, what we noticed as a part of the larger experiments was any content around the deviations, such as the email of the person whose phone number was, a text instead of an actual number, was prone to more leakage. So,
yeah, and I think we just wanted to show this as an illustrative example.
But yes, and how do you actually rectify these inaccuracies? Inaccuracy rectifying is a topic that's been super well researched upon. This is a much more simplified script, but there are libraries such as NLTK and a couple of others which have corpuses of large amounts of data specifically meant to, rectify inaccuracies. Character normalization, right? I'm going to kind of jump through the next couple of techniques, but this is so simple, but it's actually kind of funny that when you build a data set, just make sure that it's all in the same character format. If you want to go UTF-8, let's just stick with that and make sure we don't really deviate. That helps a lot more. And this is arguably the easiest production grade script I've written. Just go through your data set, encode it all in the same encoding, and that helps a lot as well. Okay, dimensionality reduction. This is where effectively, let's say your model, going back to the above example here, right? If this is your training data set where you have like 5, 6, 7, 10, 15 fields you want to train your model on, it is not necessary that you want to train it on everything. Same going back to the original one, right? Bigger is not always better. Just because you have more parts of your data, yes, context is important, but context is important to your use case when you're fine tuning, right? So you do not want to just throw at it like every field you can find in your DB. More often than not, it's better that if you choose the top n number of fields that is for your use case and fine tune your model on that. And sometimes if you have like 5 to 6 different tasks, it's better you train 5 to 6 different smaller models, each an expert in their own task, right? So that's something which we definitely notice reduces leakage. A simple script, sklearn has a lot of, again, your entire dimensionality reduction as well as a larger, more complex machine learning technique, but we've kind of simplified it as an example which we wanted to show you guys here. Augmentation. Not always are we going to have enough training data, such as in our case, we could not actually find 5,000 bits of pair of individuals. And even if we did find, we couldn't train a model on that. So in that particular scenario, we can use tools such as Gretel or other, ChatGPT or your OpenAI models, or any model to generate synthetic or fake data. But here lies, in that lies a inherent problem where when you get data from the real world, such as let's say credit card transactions, right? There is a pattern to it because we as humans, real transactions have patterns we want to analyze, or even if it doesn't, we want to understand that. But generating that kind of synthetic data might not have those patterns or may introduce patterns which are just honestly non-existent. So we need to make sure that while augmentation is great, it's really important we do it at a slow pace and validate the augmented data. With that, once again, a lot of techniques exist, but these are a couple of techniques which we found work really well. But after you have your data, what is model training? We just wanted to show you the script which we wrote, which is arguably one of the simplest scripts we used to train. Super simple. It's, under 100 lines, nothing too much. We just load a model from, Hugging Face. We use a transformers library and then just train it on the text we have. So the purpose of this slide for the most part is to display that your training of model is not hard. The more time-consuming task is in preparing the data set with which you're going to want to train the model. Mm-hmm. With that, Rob, do you want to talk about
how do you then test it? So like you've built your model now, what are some techniques you can apply to actually answer the question, like, is it doing something I don't want it to do? Is it leaking? Let's start out with the simple ones, like basically doing these types of just asking the model for the specific type of information you want, or trying to create error conditions that it may have observed in its training data, or trying to use asking it about what it's seen in the past versus current state, or asking it about itself or things that it's seen in anything that it observed in learning, or just straight up secret extraction. I think that these techniques, whenever someone's directly interacting with the model to try to get it out, are interesting. I think a lot of your customer base, though, will be more impacted if there's also the combining this issue with things like prompt injection. And the biggest issue I'm seeing in a lot of the models that I'm testing is the ability to then generate links using Markdown, where the web interface renders that link. And then there would be some part of the prompt injection that coerces the user to interact with it and then sends that information that was leaked in that response or was extracted back to the attacker. And so I think that's probably one of the most important things to test and make sure that your users aren't copying and pasting something that's going to cause a leak to easily be exfiltrated. Model inversion attacks, as they're applied to large language models, can be things like, I want to actually try to recover specific training data. So in this example with customer support logs, you may want to ask it about issues with the account or the order numbers and like whatever language that organization's using, and then seeing if it does responds with more details about that. This is like, you're going to want to craft this on like an application specific basis. And some techniques to then apply to that are things like continuations. So you can put the text where you're asking, so have you seen this before? And then continue on and it's basically filling in the blank and seeing if that was not properly cleaned from the data set, if it'll finish your sentence or finish your paragraph with something from that training data. Seeing if there's repetition of like trying to get it to repeat the same token over and over and over again, and then it might give you other information about that, or divergence. Like this is back to that, like some characters or some tokens or delimiters that are in the training set, it's more likely to leak something next to that. Or if you're doing like single token attacks. So I thought this was an interesting bit of research. So like one token will actually, you're much more likely to get leaks from like one tokens up to like repeating like below 400 times. And then as this expands, like 2 tokens, 3 tokens, like the probability of that is like more certain that you'll get like a leak in the response. Using special characters as well, like this is an example of actually getting leakage out of Mixtral as a model. So this is like a character that was designed to use as like encoding a space in the training data or encoding something into what it might consider like the end of the prompt. And so this was actually like, as you can see, that was mostly getting like gibberish out of this. So not necessarily anything useful. I think you would have to really do a lot of like repeated attempts with variations on this to get something useful, especially in black box like model inversion attacks. A lot of the research on this, researchers have copies of the training data and then they're seeing like validating if they got what they wanted out of it. But in black box testing like this, it's really difficult to know if exactly what you got out of it is that hallucination or is that leak. And I think you'd really have to be fuzzing it with a lot of traffic. So one of the things that I think is really important to be able to do is rate limiting and monitoring the usage of your endpoints and applications that are integrating with these models, and then being able to flag and shut that down as a behavior that might be trying to extract sensitive information. These are some examples of like code gen leaks. So like being able to look for identifiable information or private information or secrets. A lot of it is like anything where someone might have been defining a key or setting a password or setting commonly something in a config are things you might want to test for to see if you're able to extract something using those like continuation techniques, divergence techniques, or repeating techniques. But manually testing is only going to get you so far. I think one of the best frameworks out there for automating your testing is Azure put out this Pirate like risk testing tool for LLMs. You actually will have to code like custom to your use case, giving it a specific objective, giving it a way to score if it has achieved that objective, and having it generate variations of its prompts. And of course, you can seed that with like specific techniques that you might want to apply. You can give it like libraries of references of existing prompts to say like make variations on these, and give it whatever task you have. Like this is an example, and they have quite a few examples in their GitHub repository, which there's a link to in here, of like doing the Gandalf prompt injection retrieval. But I think this is a good way to like also automate your testing of data leakage as you're changing your fine-tuned models. So let's get into like more mitigation guidance, because I wasn't finding any really good examples of what you can do about it, other than more of the data science techniques. But I think this really does start with like have specific goals of what you want to make sure it doesn't leak out of your fine-tuned models, be able to measure and eval that, and then repeat that process on an ongoing basis. So like strategies for detecting this, like differential privacy you'll hear about. And I think like the best technique for applying that is generating synthetic data, actually giving your data science team copies of your production data to at least run their experiments on, because I think the real way that a lot of these breaches are going to happen is making copies of that data, and then like traditionally it's going to get accidentally posted in an S3 bucket that doesn't have the right permissions, or it's actually accidentally going to get emailed to the wrong person, or copies of it are going to accidentally be put in someone's private GitHub repo or private TensorFlow repo or private Google Drive. And then that's the way the breach of the production data is going to happen. So I think this is definitely valuable to apply. A couple of frameworks I came across that like have been recommending is Microsoft's Presidio data protection framework. I think this was one of the most comprehensive ones because it creates this really defense in depth pattern of like we can apply regex patterns of what we don't want to see. We can apply like more deterministic NLP models or name entity recognition models that are able to flag specific elements in your data. You can have checksums. You can have like these specific words for context that you want to alert on, or even like techniques to anonymize. The example of like the checksum might even be something like a Bitcoin address that like you want to like confirm that it's a Bitcoin wallet, and like I want to be able to flag on that. And you can extend this framework for like it comes with a lot of pre-built entities, but you can also super customize it. If you have some element of your data that you're really worried about showing up in these models, you can use this to apply either data cleansing in the pre-training part of your workflow or in post. These also have functionality to actually, if you're streaming the output of your model, to flag this and catch it. So like this is an example of like a version that's been implemented to integrate with Llama Index and being able to basically give this text in. This is the output of that. Like it's actually identified like this is a person, this is a credit card, this is an this is set in the state to actually mask these, but you can also this is a good workflow I think on both ends, but the other this is really comprehensive in that you can do things like replace it with other data, fully redact it, hash it, mask it, encrypt it. The encryption use case might be you actually want something in your workflow of output of a language model to have access to the plain text of sensitive data, but you want every other part of the in transit or any other place that data might be stored to be encrypted. And so you can actually apply this library to only have it unencrypted at the time it's being used by that application workload, and then it's back to encrypted after that. So yeah, I think this is like probably one of the most useful and comprehensive libraries. And this is actually us applying it to our model. So this is example of the same thing you saw earlier with Precious PII, and it actually redacting and actually masking the date, the person, and credit card numbers. And so like birthdays are hidden now, and no more PII leaked. AWS has guidance for how to use their Comprehend system as well. So Comprehend is their natural language processing native service. And you can build workflows with this as well of like, I want to actually answer questions about what's coming out of this. And this might be a case where you want to have some chat interface that just like throws an exception on sensitive information or even unwanted behavior coming out of your model. So yeah, I have some examples in here of how to use Comprehend. So if you then want to eliminate hallucinations, there are libraries like Outlines out there. This actually allows you to turn these generative models into like a finite state machine of per token that's generated. I want to compare this to a regex and actually guide it. And if I ever detect that it's not going to match that regex, I can event on that and throw an exception and have it go back, perhaps adapting the prompt or adapting the interaction so that it does create the type of output you want. So like you might have a use case where like, I only want the output to be URLs. So the only thing I'm going to ask it questions, but I want it to answer me in only URLs. And then you could have a regex say like, if it's not a URL, I don't want it, go back and try again, or we have some problem in our input or our prompt, and let's then adapt that. And then another popular open source framework is Guidance. And Guidance actually allows you to do things like much more contextually. So like this is an example of it detecting an anachronism, like T-Rex bit my dog. Like it actually would do the analysis of like, well, T-Rex existed 65 million years ago, dogs exist now. So like that's probably not true. I'm going to assume like this is a hallucination, and like I can event and track that in my code. So key takeaways, like I think preventing these pre-model training and post-model deployment is like your best strategy for defense in depth. The biggest thing you can do to impact data leakage is to focus on deduplication of data in your training data set that you're fine tuning on. The size and context of the size of the model and size of the context matter a lot for leakage. You have to test for this on the other end. And I think rate limiting is probably one of your best mitigation factors to see if there are adversarial or like malicious attackers actually trying to test for leakage. And then output sanitization is going to be your best like last line of defense. Again, Rob and Aashiq, and these are contacts. These are some of the resources if you want like copy of the slides. And you can play with my.precious.ll has the experiment that we ran if you want to play with those models and see what you can get them to do. And they're also hosted on Hugging Face if you want to see exactly how to interact with them there. Yeah, so thank you, everyone.
Thank you.
All right, we have less than a minute for a question. How do you ensure the generated data is not actually related to a real person?
Yeah, I think that that's a good question. I think that you'd like have to study like what was in your training set, and if it's a possibility that you had real people's data in your training set, it's a very real possibility that the output might also contain real people's info. Yeah.
And also accounting for that same, going back to the way he was talking about it, if the model is only spitting out series of tokens, it's better that you just layer like something like your Presidio and just mask out stuff stat if you do not want any semblance of PI. But if you do want some kind of content, that's going to require a more detailed use case by use case analysis.
Thank you. Thank you. If you have any questions for our guest speakers, I would recommend you meet with them after to ask them. So please join me to thank Rob and Aashiq for their presentation.
Thank you.
Thank you.
Questions on Slido, and to ask your questions, go on BSidesSF.org/Q&A. That these are the letters Q&A. At the end of the talk, we can go through your questions. Now, please join me in welcoming Joe and Chandrani with the talk.
All right. So welcome everyone to the last session in between you and happy hour. Today we're going to talk about a big question. So what if your security team could automatically fix your code vulnerabilities? So think about this. AI can go through code faster than any human, potentially finding and fixing your vulnerabilities. But we know that AI fixes are still imperfect, and we need to manage our expectations about the performance of AI fixes. According to a SW benchmark, even ChatGPT-4 could only fix about 2% of complex bug fixes. So that means we need to use AI with oversight and still keep humans in loop. And today we're going to talk about strategies for increasing our chances of finding and fixing correctly. And we're going to talk about where to focus effort. And this problem is actually two distinct issues. This is finding vulnerabilities and fixing them. And next, we're going to give you a little background on finding vulnerabilities in the traditional fashion. So traditional methods of finding vulnerabilities are going to be through manual code reviews, static application security testing or SAST, DAST, fuzzing, external bug bounty programs, incident reports, pen testing, or red team reports. The issues with this is oftentimes you have a lot of false positives generated, and this can erode developer trust when they see a potential vulnerability that isn't actually there. Additionally, you have coverage of vulnerabilities can vary depending on the type of detection you're using. This process can be time consuming, and manual reviews are slow and prone to human error. And incident reports, like the known slice there, are the ones that you don't want. And we're going to see if we can use AI in this process. And the goal state of this is we want to be able to increase our coverage and increase our true positives and decrease our false positives. We're still not going to be perfect in our coverage of all vulnerabilities in this. And there are at least two ways of finding vulnerabilities using AI. We can do an AI-only approach, and that would be just using a prompt and feeding in your code to the prompts, or we can do some sort of fine-tune model like GPT 3.5 fine-tuning. And we tried this with a few hundred examples of real vulnerabilities and fixes, and it wasn't that great. And then you can additionally use a prompt-driven strategy where you're also using that to supplement your results from SAST and use AI. And then where can you do this in the process? You can do this at the stage of pull requests, or you can check your code retrospectively. You can do your whole code base. You can do entire repos. And that's a little bit harder of a challenge, but that's what we did. But the key is you can build on your existing frameworks and not totally throw them to the wind. And now we're going to talk about non-AI fixes. So as you can see, traditional methods of fixing vulnerabilities without AI are just people in seats doing work. There are problems with prioritization. A lot of times you don't know what priorities your vulnerability should face, your vulnerability should use, and then also you need a skilled team. Fixes are time consuming. Humans are also prone to error. And then you can have an example of instances where your team issues a patch for vulnerability, the patch didn't work, your team has to issue another patch. Also, you can have the same type of vulnerability can show up across multiple repositories if a bug bounty hunter finds one and runs it across all of your different products. But using AI, we know that we can use AI to generate fixes for at least simple code vulnerabilities. And we would still have the human validate the fixes. And we still need our expert team, but now they have more time to resolve the complex fixes AI can't handle. So there are commercial solutions out there, but we're going to talk about why you might want to build your own solution. A lot of times you will almost always have proprietary coding languages, styles, and libraries. For instance, your team may have a XSS fixing library that you want to make sure that your data gets sanitized, and you don't want to depend on an open source solution where you're not sure if it's going to be maintained. There's a large cost associated with commercial solutions. If you have a team of hundreds to thousands of developers checking in code, the cost for using a commercial solution can run into millions of dollars a year. One of the most important parts is you want to be able to customize the measurability of your fixes. You want to be able to measure your historical performance based on finding vulnerabilities and fixing them. And a lot of times you have those resources at your disposal. If you're tracking your fixes through Jira and GitHub, then you can automatically extract those programmatically. And finally, you want to be able to grow internal expertise in AI. This is important because you don't want to be dependent on commercial solutions. So with this, I will pass it over to Chandrani.
Thanks, Joe. So now we talk about the solution journey. This was very new area for us. We did not really know what would actually work, what would give us a good result. So there was a lot of trial and error before we could say, yeah, okay, this is an accepted good solution. Right. And then whatever work we are presenting here and the results, they are done on the GPT-4. But then it should be language like model agnostic, the methodology. So first we started we needed to do a POC, right? We needed to establish the fact that this very thing that we are trying, that trying LLM to find vulnerability and fix it, this would actually work. So for this, what we started with a zero-shot prompt engineering method. Therein, what you do is you rely on what the model already knows, the intrinsic knowledge of the model, and you are relying that the model will give you the most optimized results. Right. So as an input, we created a dummy repo with some very obvious, straightforward vulnerabilities in it. And we were like, okay, find and fix whatever you can. Obviously, the system prompt was not as simple. Just before the talk, I think by OpenAI, they mentioned that you need to praise your model. So we did the same thing. You mentioned you are a very expert AI security engineer. You're very methodical and blah, blah, blah. So, and then it was able to find out all the 8 to 10 vulnerabilities that we had injected with a very good precision, and then it was able to find great fixes for them. So with high hopes, we wanted to apply the same technique on our production repo, right? So it still is zero shot. But then the input strategy, we changed it okay, let's go on to the production repo and let's see what it gives. On the system prompt, we are not giving any additional example or any additional context, but then we are making it a little bit advanced. That means that we looked through our Jira, we found out what are the top 15 vulnerabilities. We picked those and we are like, okay, give me only the vulnerabilities related to this. We gave a list of languages so that when it is generating the fix, it is context aware. It has that language awareness. And we also gave output response schema. So do not just give me blood out response. You give me only for these fields, only in this particular format. Right. So everything was, going great. It gave out a lot of issues in the format that we expected and all that. But when we tried to manually evaluate, when we were going through the results, the issues, there were a lot of false positives. And not only that, the fix it had generated, it was very much hallucinated, which means for example, it would say that include a sanitize function, but it would not actually include a proper definition of it. So then we kind of took it slow. We went with okay, let's give a single example to it. So single shot method is in wherein you give your model a single example how your output would look like, and you expect that your model will learn and will try to mimic that. So we changed our input strategy from going to the production code to we changed over to Jira, because in Jira we already have our vulnerabilities logged in. There are vulnerable code snippets that have been exploited, so those are also logged in. So we took that as an example, and there is also a related repo that is written in this repo we have found out. So we are giving a one code example and the related repo. Right. So here what we saw is if it is very similar, if the code is very similar, it is able to detect that. But then variable tracing within the same file was still a problem. Like for example, if the variable has been defined somewhere, later it's accepting input, and then finally it has been used as window.out, URL and all that, it is still not able to make all that context. That was the one. And then also, even for like we have given one particular example of injection, but if it's injection and if the code is a little bit different, XHR related or stored injection, it's not able to detect properly. So then we moved on to the few shot method. Few shot is like when you not give just one, but like 3 to 5 examples, so that the model understand the context and the task better. So here we look through like, okay, in our Jira, if we say injection, like what are the different types of injection examples that we can find, and let's give that and see what how we are saying. Right. So here basically multiple injection examples you are giving. With this, we were seeing improvements in detection, in finding the vulnerabilities, but we would say that there was still a lot to go. What we could say an accepted fix. So almost at the same time, we came across a paper that was by Boston University that talked about this chain of thought method, wherein they have mentioned that they have done vulnerability detection with about 70% precision rate, wherein so this is basically how it works is you have a problem statement and you are explaining what is the problem. If you are giving a decision to the model, then you are also explaining like why you are taking the decision. So basically you are you want the model to think the way a human would think, and it would mimic that entire thought process. So here we are not only giving the Jira ticket summary and the description, but we are also giving an explanation. Like for example, here is my vulnerable code snippet. Then next I'm giving that why I think this is vulnerable. So I'm explaining like, okay, this param input is coming from user input. If a malicious JavaScript is loaded, then when the window.url gets executed, that gets executed in your in your environment. And then I'm giving a proper fix. So I'm not only giving like sanitize this, but I'm also giving a like proper definition of that, like how that sanitize would look like, right? And I'm saying like why that that fix would work. So with this this kind of thing, and for like we mainly tried, so for the injection we saw a lot of improvements both in detection and the quality of the fix that it was generating. But I should definitely mention that it is not for vulnerabilities that is spread across multiple files. It is for vulnerabilities that is contained within the same file. So reality check, definitely like from the point when we started with the dummy repo, it gave everything perfectly. Everything was able to, all the issues were, it was able to found 10 out of 10 till the point where we are today. There was a lot of realization. Right. So challenges, as I mentioned, like for example, the complex vulnerabilities, like whenever it is spread across multiple files, multiple repos, then GPT would do really poorly. Then when we moved over to the production file, production repo, there is no proper test file, right? Because you never know how many vulnerabilities are out there in your repo. We have static code checkers, but we all know that also produces false positives. So if you are if the my model is producing 10 issues, I do not know if the 10 is out of 100 or if the 10 is out of 20. So you never know the denominator. And then the correctness of the fix, right? So this is also like very subjective, like how deep, how accurate you want your fix. Like for example, if you are using a function, if you're saying that you need to include a function, the proper function definition should be present. If there is a place for constructor, if there is an import statement, all those should be included as part of the code fix, right? It should not just say include this. There should be library imports of this. So there should be proper code for those. So how much deep we would go with the fix. So those are also like subjective. So next we move on to metrics and evaluation. Initially when we started this, obviously we started with a manual evaluation. We will go through each of these findings and we would see like whether it's a correct fix, if it's a correct fix, whether the fix generated is, is good enough. But then obviously with manual evaluation, you cannot scale. That's not accepted. So what we tried is the auto eval framework. So this is something LangChain provides. They have a lot of like eval framework, eval APIs or functions that they provide. The particular one that we used is the scoring evaluator. So basically what we did is we initially created a data set with vulnerable code and the corresponding good fix. We called this as a golden data set. And then we would take that same vulnerable code and run it through the LLM and it ask it to generate a fix, right? And then we would compare like how close that fix is with respect to the reference fix. And this is where that the LangChain accuracy calculator comes into picture. So basically it lets you define the accuracy on a scale of 1 to 10. 10 means like you're fixed the predicted one and the like the reference one, they're very context wise and everything is very similar. 7 means there are minor differences and so on. So we decided like, okay, if the accuracy is looking like closer to 70%, we can say like, yeah, this is a good enough to go. And then we can accept the prompt and we go ahead with that, like generate code fix of similar type in other repos. For metrics, there are two types of metrics that we have considered so far. One is the precision, right? So precision is like if you have 10 issues, but you have only 4 of them are correct. So your precision is then 40%. And then accuracy, like how good your fix is. So with like all these methods and like prompt engineering methods that we have tried, we found that with chain of thought, it is giving us more promising results. Yeah, and then we have a demo. Over to you, Joe.
Yeah, so there were 3 different ways that we implemented this. First, we did a code fixing directly from a Slack-powered AI agent. And we also had an option of implementation where we had a CLI-based infrastructure where we would iterate over entire repos and then select and improve fixes for PRs later. But this one is the most simple. And this is just a simple command line where we issue the PR directly. And this is very short. It's about 25 seconds. So this is the fix happens and it explains the fix and why, what was vulnerable. And then this is the PR. And yeah, that's about it. So conclusions. We had quite the journey, and it's still ongoing. So for people who aren't familiar, this is representative of the Gartner hype cycle. So it's where your expectations are over time. So when I first saw this a few years ago, this really resonated with me. So when we started off at the beginning, we had our POC. And we had a lot of expectations. I thought this project would probably take a couple weeks, and we'd be done with it. And then when we started moving up with increasing code difficulty, increasing vulnerability difficulty, we still thought we could handle it. We did zero shot, we did single shot on real code, same with few shot. When we got to chain of thought, we were still getting the fixes we wanted that actually aligned with historical fixes using our proprietary code and libraries. They weren't just generic fixes, and we thought that this was great. But as the complexity of all the vulnerabilities and the different coding styles and the different files kept going, we were still using this manual evaluation process, and we realized that this was not a sustainable thing. And then when we transitioned over to the auto eval framework, that was, we realized that we were at a place where we're going to be moving up, and there's actually a path forward. So now we're at the point where we are we have a clear path to full productivity. And some prompt strategies that we learned along the way that ended up being pretty valuable, we'd like to share. So the first one is you always want to reduce opportunities for LLM laziness. And what you see in the upper right-hand corner there, that's an actual function provided that's supposed to be a fix from GPT-4. So that's not what you want. So your prompt should contain something like placeholder comments, ellipses, and other shortcuts will never be used in place of functional code, and maybe more than once. The second strategy is you want to make sure that you have your proper output schema. You want to include your file formats, the schema details, and how you want your output fields. So this is just a snippet of a couple of fields you might want. And even if you have this specified, you still may get syntactically incorrect output from time to time. The final one is you want to reduce opportunities for LLM hallucinations. So you want to have output fields that the LLM can generate into instead of hallucinating. So having library imports as a field or method creation for a field. Or you can have language-specific fields that would only be used in context of a specific language, like constructor changes or something like that. And some key takeaways. Directed fixes are helpful. So the more hints you can provide to your LLM, the better your fix is going to be. And finding and fixing uncomplicated vulnerabilities is a simple task for an LLM. And this may seem obvious, but fix things that are 100% known to be vulnerable first. For instance, if you have results that are validated from a bug bounty program, you can use that as input to your prompt and get a fix quicker that way. Metrics are key. So regardless of whether you build or buy, you want to measure the effectiveness of fixes for your code. And so traditionally when you do evals, it's pretty simple. You have a question, you have an answer, and it's pretty easy to think about. But when you're trying to do evals with code, you have to think a little differently because code is not human language. So for evals, your question is your code and your fix is the answer. And your answer can depend on how narrow your question is. How much information do you want? And fine-tuning prompts can take you pretty far. Chain of thought, as we saw, was the best for performance. And well-designed prompts and output schemas are key. And lastly, humans are still gatekeepers, and you always want to keep humans in loop for final validation. That's it.
All right. The audience has a few questions for you guys.
Okay.
First one, nice work. How do you manage the accuracy of the AI code fix? Do you maintain any evals data set?
Yeah. So we track all of the fixes and all the results we track in a table, so that way we can measure the performance over time.
The second question is, why not use SameGrep, which is open source?
Yeah, so a lot of times, so we have an internal solution that we can take the results from our static analysis and feed that into the LLM. So it's kind of like you're adding an additional filter on top of your results.
Which one was more effective, finding vulnerabilities or fixing them using AI?
Fixing. Yeah, fixing, because when you're trying to find something, it's pretty greenfield. You can look through an entire file, and a lot of times the LLM would generate a lot of false positives. A lot of times it'd be good at finding vulnerabilities, but it would find things that weren't there too. So yeah, the fixing, if it's more directed, if it had something more narrowly focused to look at, then it could do better.
What kind of vulnerabilities here you have experimented with?
Yeah.
Yeah, we have mainly tried with XSS injections. Yeah.
How does it handle when the fixes require a complex code fix?
Can you say that again?
How does it handle when the fixes require a complex code fix?
So yeah, I can take it and then you can add.
Totally.
You need to give a lot of details, like for example, specific to your company, what all standards it follows. So sometimes in the system prompt, you need to give those details as well. And then you need to mention in your output parsers, like where exactly you want, if there, like Joe mentioned, the import statements, if there are constructors, if there are functions, where exactly you want them to be placed. So it really depends how fine-grained you can make your system prompt. You want to add something?
When you do few shot, do you retrain the model or just provide the samples as context?
So we have something set up that was like, I called it an adaptive few shot. So depending on the type, if we knew the vulnerability type ahead of time, it would pull out the few shot examples from a known set of that particular vulnerability type.
How do you mitigate any security implications of giving AI access to production?
So we always would only issue PRs, so nothing would ever go to main. Yeah.
Have you considered any semi-automated feedback mechanism so the LLM responses can be refined over time in a scalable way?
Yeah, that is there in our plan. Like, for example, right now it's very much Jira driven, the flow we have done. So probably something like Jira comments, and then that incorporate that in the LLM in the backend. Yeah.
Were you worried about sending internal code over to external model APIs?
That's a great question. We did everything through Azure, OpenAI, our own company's instance. We would have been, that was something we would have been concerned about normally.
All right. These are all the questions we have on Slido for now. Please join me in thanking our guest speakers.